All right, let's take a look at example 9, which is another cubic equation of state problem. So again, I want to remind you that on Canvas, we have a page, right? And in this page that's posted in the Chapter 2 module, I have material which I've created previously, several years ago, matter of fact, that's been posted on YouTube of code that I've written to perform calculations using van der Waals, SRK, and Peng-Robinson cubic equation of state, and then a script to demonstrate their use, for example, 211 from the text. I would encourage you to use my MATLAB code, right? Again, my goal isn't for you to spend hours writing MATLAB code, debugging it, and things of that nature. What I want you to understand is what an equation of state is, how you use it, how can you use it, more of the concepts, okay? We can get through most of this class just working with tabulated properties. The goal is you graduate, you become a design engineer. It's important to know the tools available to you to solve problems, right? And especially in chemical engineering, cubic equations of state are indispensable for process design. Same is true in mechanical engineering. Say you're trying to design some new refrigerant for Whirlpool or another appliance company. All right, so water is great. Most of the problems in this class will involve water, so we'll use tabulated properties. But for everything else where data isn't necessarily tabulated, cubic equations of state are going to become an indispensable tool for you to use. Key thing I want you to remember is here we're going to be using cubic equations of state in their normal way, if you will, right, where the goal is for given temperature and pressure to calculate V or Z. And so, again, what I really want you to remember is, how you use the cubic equation of state is for given temperature and pressure. Okay, for my fluid, I can look up Tc, Pc, and omega. All right, these become my inputs to my black box, all right, which is my MATLAB code in this case. And out comes Z and V. All right, so essentially I'm calculating Z with my cubic equation. V I can get as a result as well because V is equal to Z RT over P, right, where I specify T and P. What the key is going to be, and actually what we'll do first as we work through this, is if I'm near saturation, I can get up to 3 real roots. So what's key then is understanding how my black box works and then working with the results. And so the key is going to be if I get up to 3 real roots, I need to know what phase I have. If I have a liquid, then I'm going to choose the smallest Z and V. If I have a vapor, I choose the largest Z and V. If I have a two-phase system, I use the smallest to represent the saturated liquid, the largest to represent the saturated vapor. Okay, you always throw out the middle. Okay, there are other iterations. I could say specify Z and T, and then you could have to iterate, but those just become numerical exercises. All right, so before we even begin, let's just go through. We're asked to calculate molar volume of isobutane for a range of conditions. So what I want to do is just one more point is when using my MATLAB code, okay, whenever you're working with thermodynamic expressions, you need to make sure you're using absolute temperature. The exception may be sometimes you'll get an equation such as an Antoine equation, which explicitly says temperature in degrees C, and the conversion factor is built into a constant. Okay, but in general, you're always using absolute units. If you're using my code, I want to make sure you're using absolute units of Kelvin. And for pressure, make sure you're using units of bar. Okay. All right. So we're going to calculate molar volume of isobutane at a range of conditions. So first thing I'm just going to do is I'm going to go through A, B, C, and D. And I want to identify what phase we have in case we have this situation where we have more than one root. Okay. So we're told that at 30 degrees C, or the saturation pressure at 30 degrees C is 4.05 bars. So if I'm at the same temperature, but my pressure is less than the corresponding value of saturation, I have a vapor. If I'm at the same temperature, but my pressure is greater than the corresponding value of saturation, I have a liquid. Okay. Then here we're told saturated liquid, saturated vapor. And so what I'll do in case C and D is thinking in terms of my black box, is we can use the cubic equation of state to predict coexistence. All right, so if we were told we have coexistence and we have this T, we could solve for the pressure using that cubic equation of state. But we're not there. That's actually a topic in Chapter 7, which we won't get into in this course. Okay, so for this problem, I'm going to plug in the reference value of a pressure of 4.05 bars, and then I'll pull off the liquid, so the smallest root, and the vapor, the largest root. Okay. All right, so hopefully this one's straightforward. Again, review the example posted on MATLAB to demonstrate the use of the code, and we'll start with that code here, and I'll demonstrate modifying it for our problem. Okay, so I've over MATLAB. So again, I've got example 211. This is the one that's posted on Canvas, and then I have my functions for computing molar volume for Peng-Robinson, SRK, and van der Waals. So what I'm going to do for this problem is I'm going to base it off of 211. I'm going to start by saving this as. All right, so I'm going to create a copy, and this is going to be, so I'm calling it Chapter 2, Example 9. Okay. I'm going to delete a bunch of this top stuff. Okay, I'm just going to add a comment that this is for isobutane. All right, so hopefully this is pretty straightforward. So the first thing I'm going to need to do is I go to my the appendix, and let's find isobutane. Where are you, isobutane? Isobutane's here. Okay, so for isobutane, I need critical temperatures 407.85. Okay, critical pressure is 36.40. And the eccentric factor is 0.186. Got it. Okay. And then we'll update this for each part, but let's kind of modify this then. So all I need is the molar volume. So my SRK code returns molar volume, compressibility, and the molar volume of my ideal gas. The volumes are in units of centimeters cubed per mole. Okay, and I'm going to update it so that I just get molar volume back. And I'll call this one, say A, since it's part A. Okay, so let's do this. Okay, so I'll call this part A. So in part A, let me slide this down. We have temperature of 30 degrees C in 1 bar. Okay, so I'll just type in 30 plus. All right, so I need to convert to Kelvin. Pressure of 1 bar. And that's it. Okay, so critical constants, my temperature, which I convert from Celsius to Kelvin, so I just add 273.15. There's my pressure. Here's me calling the MATLAB code, right? The function that I shared with you. Haven't changed the names of any of these variables so that this call doesn't need to change. Okay, so when I run this, okay, I get 3 real roots. And here, right at 1 bar, we said we have a vapor. Okay, so I'm going to want the largest root. And so if you notice, these are already sorted. Okay, so let me create a variable to store our final result. And they're sorted. I want the largest one, so I want the first entry. Right? I could also use max, but roots already sorts them, so it's there's no need. Right? So cool. And so the units here are centimeters cubed per mole. So now if I want to do this for part B, okay, let me just copy and paste. Okay, so part B, the temperature is going to be the same in all of them, so I don't need to actually change the temperature. Just need to change the pressure. The pressure is now 10 bars. So first one we have a vapor, this one we have a liquid. bam, bam, and now, well, let me comment this out for now, and let's see how many roots we get. Okay, so I get 3 real roots again. I want, I have a liquid, so I want the smallest. Remember the pre-sorted, so the smallest is the last. So I'm going to want the last value. Okay, end, right? Or I could use 3. So for B, 114.2760 centimeters cubed per mole. For C, okay, we're at saturation. So for C, the pressure we're going to use is 4.05. Okay, so I'll store this to C. And, okay, let me delete this. Let's see what we have. So for C, right, I get 3 roots. Okay, so if I want to separate them out, so if I say VC vapor, right, is going to be the largest one. And so that would be the first element. And if I want the liquid, it's going to be the smallest. Which is the last. Okay, so here's part A, here's part B, and then for the last part we have a saturated or two-phase mixture. Here's the vapor, and here's the liquid value. Okay, that's all there is to it. Okay, so key is just becoming comfortable using the MATLAB code, and then working with it and being able to identify the phase so you know which value to use. Okay. Again, this isn't a MATLAB course. I use MATLAB to make life easier. All right, that's it. Okay. Feel free to use my cubic equation of state code. The goal is for it to help you, because I want you to focus on learning what an equation of state is, how to use it. So in your future life, if you're trying to model some refrigerant for which data isn't tabulated, the light goes off in your head of, hey, I can just look up TC, PC, and omega if it's available, and use a cubic equation of state, and use that to estimate and predict properties. Hope that helps.